Let us now collect all the ingredients of the prisoner's dilemma as it has been described before. First, who are the players? We know that there are two players. These players are the two potential prisoners, the two convicts, and therefore we can label them by player 1 and player 2. And that's what we do. So in the notion of this course, we have that capital I is 2. Again, capital I denotes the number of players, and the set of players is given here by the set 1, 2. Each player in the game has exactly two strategies. He can either cooperate with the other player and not tell the police anything, or he can defect from such a cooperation and tell the police about the other player's involvement in the crime. So each player therefore has exactly the same strategy set. That means S1 is equal to S2, and this set consists of exactly two elements, one for each potential strategy. That means the strategies are C and D, and they therefore are the set of strategies, the strategy sets of the players. What are the payoffs? What is it what the players are interested in when they play the game? They are interested in minimizing the number of years in prison. In my course, the notion is that what players do is they maximize their utility. So what it means is clear that they have a higher utility if the prison sentence is lower, is shorter. So utility is maximized if the prison sentence is minimized. As we have to express everything in terms of utilities which we can maximize, I will therefore just say the utility of a player is minus the number of years he is sent to prison. And then clearly if he maximizes this, he will minimize the prison sentence. So let's look first at the utility of a player if both players play the strategy C, if both cooperate with each other and don't tell the police anything. In that situation they are just charged and found guilty for petty theft and sent to 1 year's prison sentence. So the utility of player 1, if player 1 plays C and if player 2 plays C, is the same as that of player 2 if player 1 plays C and player 2 plays C, and it's given by a 1 year prison sentence, which translates into a utility or a payoff of -1. In the next line we have the situation where a player, for example player 1, is cooperating, but the respective other player does defect and tells the police. So that's the worst situation that can occur for a player. So for example for player 1, if player 1 does cooperate with the other player, but the other player doesn't, the other player defects in the sense that we explained before, then the original player, player 1, gets 20 years in prison. Okay, obviously it's the same payoff that player 2 would get if player 1 defected and he himself would be cooperative. So now, if player 1 is the one who is telling the police about the other player's involvement in the crime and the other player is trying to be cooperative with player 1, player 1 will walk away without any prison sentence and therefore his utility is 0. And respectively, for symmetry reasons, you have that also the payoff of player 2, if CD is played, is also 0. So what remains is the payoff if both defect. That means if both tell the police about the respective other players' involvement in the crime, then we said that both get a 15-year prison sentence, so the payoff would be -15. So all these components of the prisoner's dilemma can be represented and can be drawn into a matrix. That is what we call the normal form or the matrix form of this game, of the static game of complete information. We have all the ingredients here in this matrix. We have the players. Player 1 is here, player 2 is here. Player 1 is what we call the row player, because player 1's strategies are the rows of this matrix. There are two strategies of player 1, and therefore we have 2 rows in the matrix. We have the defect and we have the cooperative row. And then there's player 2, and player 2, as he also has 2 strategies, and as player 2 is the column player, and therefore his strategies are the columns of this matrix, we also have two columns, one for defect and one for cooperate, for C. And within this matrix we can see the payoffs of the players in terms of utilities. So for example, how do we read this matrix? If player 1 plays cooperate and if player 2 plays defect, plays D, then the respective or the according payoff would be here. That is where defect and cooperate come together. And the payoff of player 1, that's the first number, is minus 20 years in prison. And the payoff of player 2 is 0. That means no prison sentence. So this would be the respective payoffs of the players. Red for player 1, blue for player 2. The first number is always for player 1, the second number is always for player 2. Before we get interested in what the players are doing, let's first look at whether there are Pareto optimal outcomes in this game. First, there are 4 different outcomes in the game. It could be that both defect, it could be that player 1 defects and player 2 cooperates, or the other way around, player 1 cooperates and player 2 defects, and could be that both cooperate. So the 4 outcomes are associated with the 4 different cells in this matrix. Is any of them Pareto dominant or Pareto optimal? Or do some of these cells Pareto dominate other cells? What we can see first is that the cell that is defined by DD, so that would be this here, that this is Pareto dominated by CC. Why is that? That is because CC makes both players better off than DD. Minus 1 is better than minus 15, and both players here are better off than here, than in defect. So that means that DD, defect, cannot be Pareto optimal because it is Pareto dominated by some other outcome. Or in other words, some other outcome is at least as good as DD for all the players, and for some even better. Actually, CC is strictly better for both players. So what about the remaining outcomes? Let's think first about what we all probably would expect to be Pareto optimal, and that is minus 1. That is actually cooperate. So is there now some other outcome where no one is worse off and some players are better off? The answer is no. I mean, clearly in defect, both are worse off. And in defect cooperate, that is in this one here, it is true that player 1 is better off because he gets 0 rather than minus 1, but the other player is worse off. So defect cooperate does not Pareto dominate CC. And the same is true for CD. CD also does not Pareto dominate CC, so therefore CC is also Pareto optimal, or therefore CC is Pareto optimal, not also. So CC is a Pareto optimal outcome of the game. The same is actually true for CD and DC. Okay, CD, which is here, is also Pareto optimal because again, none of the other 3 outcomes is better for all the players, or at least as good for some and better for all the other players. So if you compare CD here with defect, what you can see is defect is actually better for player 1 than CD, but for player 2 it's much worse. It's minus 15 as compared to 0. And the same is true for all the other comparisons. If you compare corporate defect here with CC, what you see is that whereas CD is worse for player 1 than CC, for the other player it's the other way around. Okay, so again, we have no Pareto dominance here between CD and CC. In particular, CD is not Pareto dominated by CC, and as CD is not Pareto dominated by any of the other outcomes, it is Pareto optimal. And for symmetry reasons, that is also then true for the outcome DC. Let us next talk about what the players, or what we would expect the players to do in the prisoner's dilemma. What are the optimal strategies of the players? What is a Nash equilibrium? Or maybe there's even a strict dominant strategy equilibrium in this game. So to do this, the first observation is that it is indeed true that a player here in this game has a strictly dominant strategy. Consider player 1, and a very similar argument then follows for player 2 because they are both symmetric in this game. If player 1 looks at what player 2 could do, there are two alternatives. If player 2 chooses D, what is the best player 1 can do? If player 2 chooses D and player 1 plays D as well, he gets 15 years in prison. But that is still better than getting 20 years in prison, which is what he gets if he chose C. So in other words, for player 1, D is the best response to the strategy D of player 2. If player 2, on the other hand, played C, player 1 still believes that D is the best he can do, because D would give 0, which is better than playing C, which in that case gave him -1. That means no matter what player 2 does, whether player 2 plays D or C, playing D is always the best response for player 1. That means player 1's strictly dominant strategy is D. It is the best player 1 can do independently of what player 2 does, no matter whether player 2 plays C or plays D. So D is player 1's strictly dominant strategy. First, it does exist in this game, and second, it's the strategy D. And thirdly, because the argument is completely symmetric, also player 2 has a strictly dominant strategy, and that is also D. So what does it mean? If in a game, every single player, so in this case 2 players, any of the 2 players has a strictly dominant strategy, we have a strict dominant strategy equilibrium. And that is given by DD. It is also a Nash equilibrium because any strict dominant strategy equilibrium, as we already know, is a Nash equilibrium because you play a best response with respect to the strategy of the other player. So therefore DD is a Nash equilibrium and DD is a strict dominant strategy equilibrium of the prisoner's dilemma. And it's the only equilibrium of the prisoner's dilemma. What is interesting now is that at the same time, the outcome DD is the only outcome of this game that is not Pareto optimal. So you can see that Pareto optimality has nothing to do with Nash equilibrium or any of the equilibrium concepts we will have in this course. It is actually true that if the players individually maximize their own utility and act in such a way, they will in the end find themselves in a situation where the only outcome that is really not in their interest, in their common interest, the only one that is really Pareto dominated, will be achieved. Just as a side note, this is why this example has become so important to economics. In a sense, it is one of the few early examples of a complete market breakdown. In the sense that here's a notion that people who come together as rational decision makers and interact in a kind of like free way where they each maximize their own utility and don't care about the other, that this will lead in an optimal outcome. This notion here is really churned ahead and it will actually lead to the only outcome that we can safely say is not optimal. So in a sense, that has been one of the first examples where individual decision making leads to the worst and not the best, which at the time has surprised and astonished many people who still believe that if we would expect people to behave in their own interest, that would be in aggregate then also the best for everybody.